So I've had a lot of requests to find out how I made the sound of hydrogen for the sound of hydrogen video. So this week I figured I would do a little tutorial to show how you actually create that sound. I'm going to be using Mathematica, but you can use any software that can synthesize sounds. In Mathematica, the sound synthesizing command is just called play. So you can play a sine wave at, say, 440 hertz. So play from time of 0 to, say, 3 seconds. And it sounds like a sine wave. We can also play, say, an A880, which is an octave higher. And if you want, you can do crazy things, like playing the sine of t squared. Or even the sine of t squared. So that's a lot of fun, but we're interested in maybe some more slightly realistic sounds. So we will, instead of just playing a single sine wave that sounds like pretty boring, we might want to simulate an instrument string. So we'll do a sum over sine waves using the harmonic series. So we'll just multiply the frequency inside by n, and then sum from n equals 1 to 10 maybe, and add that up. That's kind of an annoying sound because violin strings or guitar strings, actually, the higher harmonics are quieter than the lower harmonics. So if we modulate the amplitude of each of these sine waves by something like 1 over n, we might get a slightly nicer sound. Also, we can set the sample rate to be something a little bit more appropriate. It starts off default as 8,000 hertz, but maybe you want it to be something like 16 or 32,000 hertz, and that'll make the sound a little bit higher fidelity. So that's basically the sound of a really crappily synthesized violin. For the sound of hydrogen now, we need to use the Rydberg formula instead of the normal harmonic series. The Rydberg formula is 1 over n1 squared minus 1 over n2 squared. You can look this up online to see the physics behind it, but basically just gives you the spectral lines of hydrogen. And depending on what n1 is, you can get different series, like the Lyman series, the Balmer series. So for the Lyman series, we will play the sum of sine of 1 minus 1 over n squared times 2 pi t, also times, say, 440. We'll modulate it to an A, and then we'll add that up from n equals 2, because that's where the Lyman series starts, to, say, 10. You can go all the way to infinity if you want, but it will take your computer a long time. And time again from, say, 0 to 3 seconds. Play that. And doesn't sound too shabby. A lot like our sound of hydrogen from the video. But if we want to, we can add in another series. So instead of just the Lyman series, we can add the Balmer series, which is 1 over 2 squared, which is 1 over 4. And then n here has to be n plus 1, because we start at 3 rather than 2. Now if we play that, we'll get a lot more bass. Sounds closer to our original sound of hydrogen. But what I actually did for the video was I went to the NIST website and the NIST Atomic Spectra database and got the actual spectrum of hydrogen obtained from experimental results rather than just using the Rydberg formula. So this is the exact spectrum that we see for hydrogen, and actually the amplitude as well, how bright each of the lines are. And I downloaded it. It's free. You can download that data. You kind of have to mess around with it to get it to look anything intelligible. But I brought it into Mathematica and normalized it, and then you plug that in and you get the sound of hydrogen. So I hope that you've enjoyed this tutorial, and go and use your math software to do fun stuff like make crazy sounds.